Welcome everyone, and thank you for joining us today. I'm excited to introduce our topic, insulation testing, from concept to predictive maintenance. In this presentation, we'll explore the fundamentals of insulation testing, cover different methods from low voltage to high voltage techniques, and see how these tests help us predict equipment failures. We'll also look at step-by-step procedures, some practical formula examples, and how trend analysis plays a crucial role. So, let's get started and discover how insulation testing can improve maintenance strategies and keep our systems running smoothly. Let's dive into the concept and purpose of insulation testing. The main goal here is to detect any insulation degradation before it actually leads to a failure. This is crucial because early detection helps prevent more serious issues down the line. Now, to perform these tests, we typically use a tool called a Megohmmeter, which applies a voltage in the range of 500 to 1000 volts DC. This voltage helps us accurately measure the insulation resistance. Speaking of measurements, there's a simple formula we use. Resistance in megohms equals the voltage applied divided by the current measured. So, if we apply 500 volts and see a current of 10 microamps, the resistance would be 50 megohms. It's also important to note that we refer to standards like IEEE 43 and IEC 60034 to ensure our testing procedures and results are consistent and reliable. Overall, insulation testing is a vital part of maintaining equipment health and ensuring safety in electrical systems. Let's talk about testing low-voltage motors, specifically those at or below 690 volts. The first step is always lockout, tagout, or LOTO. This ensures the motor is completely shut off and safe to work on. Next, we need to disconnect the power cables to eliminate any risk of electricity flowing during our test. Once that's done, we apply a 500-volt DC test voltage across the motor's insulation. This allows us to measure how well the insulation is performing. After applying the test voltage, we record the insulation resistance, which is a key indicator of the motor's health. Now, it's important to compare this resistance reading with a baseline value. The rule of thumb here is that the minimum insulation resistance should be at least 1 megohm per kilovolt, plus an additional megohm. For example, for a 690-volt motor, the minimum resistance should be around 1.69 megohms. This method helps us ensure the motor's insulation is in good condition and safe to operate. Remember, consistent testing and comparison with baseline values are crucial parts of maintenance and safety protocols for electrical equipment. Now, let's talk about testing medium and high voltage motors, specifically those in the range of 3.3 to 11 kilovolts. When performing these tests, we typically apply a test voltage between 5 and 10 kilovolts direct current. It's crucial to discharge the motor to ground both before and after the test to ensure safety and accuracy. A key part of this process is measuring the polarization index, or pi. We do this by taking two resistance readings, one at 1 minute and another at 10 minutes. The pi is calculated by dividing the resistance at 10 minutes by the resistance at 1 minute. If the pi is 2 or higher, that's a good sign, indicating the insulation is in good condition. If it's between 1 and 1.5, we should proceed with caution, as it suggests the insulation might be deteriorating. For example, if R1 is 50 megohms and R10 is 120 megohms, then the pi would be 120 divided by 50, which equals 2.4. That's a solid, healthy reading, confirming the insulation's integrity. Remember, these tests are vital for ensuring the reliability and safety of our motors, especially as part of our overall maintenance and condition assessment strategy. Let's talk about testing on air and refrigeration compressors. First, it's crucial to disconnect the control wiring and isolate the motor leads before testing. This helps ensure accurate readings and safety. Next, you'll want to test the windings to ground and interwinding resistance. Now, generally, an acceptable resistance value is 20 megohms or more, especially in dry conditions. If you measure less than 10 megohms, it indicates there's a problem, and it's best to perform heating or drying before attempting to restart the compressor. To understand what these resistance values mean in practical terms, You can use the simple formula I equals V over R, for example. If you have 500 volts and a resistance of 25 megohms, the leakage current would be just about 20 microamps. That's a very low leakage, which is good. This testing process is essential because it helps us identify insulation issues that could lead to failures. Remember, maintaining proper resistance values is key to ensuring reliable compressor operation and safety. So, always follow these steps carefully as part of your overall maintenance and troubleshooting routine. Now, let's talk about evaluation and trend monitoring. It's important to track insulation resistance on a monthly or quarterly basis. By doing so, we can identify any significant changes over time. For example, if we see a trend of decreasing resistance, specifically a drop of around 20%, that serves as an early warning sign that something might be wrong. Integrating this data with your CMMS or predictive maintenance dashboards really helps in making timely decisions. You can visualize these trends alongside other critical data points for a comprehensive view. To quantify the degradation, we use a simple formula. Degradation rate in percentage equals the previous resistance value minus the current resistance, divided by the previous resistance, then multiplied by 100. So, if the resistance drops from 100 to 80, the calculation would be 100 minus 80 divided by 100 times 100, which equals 20%. This approach allows us to proactively address potential issues before they escalate, ensuring the reliability and safety of our equipment. Monitoring these trends consistently is key to effective asset management.